is taken from a fashion website which is called ikon.jp. So this is a Japanese website where a lot of fashion bloggers come and make outfits and share it with everyone. So it's like a fashion
Okay.
blogging website. So we've taken that these outfits and the items in these outfits are compatible for that user, for the fashion blogger who has composed it.
Right. Also, does it take the seasonal changes also into account, like the summer and the winter? The choice of clothes would be different. Is that also taken into account?
Right now, not as such. We've not taken that factor into account specifically. But yeah, if you give like a sweater as the top and you give the bottom for that, maybe the recommendations will be according to that because a sweater would be made in a specific way by the different fashion bloggers as they compose the outfits.
Right, right. Okay, I think thanks for clarifying, Sejal.
So, if are we having any more questions from the audience? If not, let's thank speaker again for the nice talk. And now we'll be moving to the second talk of the session, which is multimedia document mining using sequential multimedia feature patterns. So over the speaker now.
So Puspalata, you can present your screen now. You have the rights. Puspalata, will you be doing the presentation or someone else? Puspalata, can you hear us?
Yes, sir. I think unfortunately suddenly the net got disconnected. Now
No
it's connected.
issues.
Yeah.
So now you can share your screen.
Okay, sir. Yeah. Thank you. Sir, is it visible, sir?
Yeah, it is visible. Probably you can use full
Yes.
screen mode.
Yeah.
Yeah, slideshow mode.
Yeah. Okay. Okay. Shall I continue?
Yeah,
Yeah,
please.
you can start. Yeah.
Okay. Okay. Good morning, Chaser, and good morning, all the panelists and attendees. I am Pushpalata from Sahyadri College of Engineering and Management, Bangalore, and our paper is co-authored by Professor Anatharana V.S. from NITK, Suratkan. Okay. Now I am going to present our paper, Multimedia Document Mining using Sequential Multimedia Feature Pattern. Okay. The outline of today's presentation includes introduction, related work, sequential multimedia feature pattern mining, experiment result, and the conclusion. The evolution in multimedia technology has led to the ubiquity of multimedia documents. Multimedia document mining help in extracting the meaningful patterns from the documents and provide the useful knowledge for various applications. The use of multimodal data of multimedia documents reduces the ambiguity and provides more information to understand the multimedia concept. For example, the word tiger may be the person's name or an animal or airways name. However, the integration of word tiger and tiger image confirms that the concept is about tiger. Similarly, the integration of the visual and audio information helps in discriminating the birds, crow, and Asian coolie. So in many applications, one modality of data may coexist with other modalities. Therefore, the integration of multimodal multimedia data will be advantageous in increasing the efficiency of knowledge discovery process. With multimodal data, the feature pattern rich sequences play a major role in discovering the knowledge. For instance, in order to retrieve the images that has forest and water, it is advantageous if the features are compared sequentially. That is, initially images are compared with forest features and then with water features. In order to use, the sequential pattern of sounds need to be extracted to recognize an event. Hence, the feature pattern sequences are used to discover the contextual information of the multimedia data. So in this paper, we propose a sequential multimedia feature pattern mining for multimedia documents. The proposed sequential multimedia feature pattern mining includes three steps. Initially, the multimedia documents are represented using multimedia feature pattern tree. Then, from the representation, sequential multimedia feature patterns are extracted. We are extracting again multimedia class sequential rules for the classification of multimedia documents. Multimedia document representation is the most important preliminary step of multimedia mining. In order to extract the sequential feature patterns, it is required to represent the multimedia documents based on the feature patterns of the multimedia documents. The multimedia feature pattern tree, that is MFPT, is a compact representation that represents the multimedia document based on the sequential feature patterns of multimedia objects. We expanded this representation for the extraction of sequential feature patterns. To cope with the multimodal nature, initially the multimedia objects are represented in a unified feature space using the multimedia to signal conversion method. So this method represents the multimedia objects in frequency domain by converting them as signal objects. Then the multimedia documents are represented using MFPT representation. The MFPT is a rooted tree having the branches to represent the signal object is of a unified multimedia document using the feature values. The tree has branches which have again feature nodes to store the feature values of the signal object. The number of the feature nodes in a branch equals to the number of features of the signal object. The branches or the tree is constructed based on the similar sequential feature patterns of the signal objects. The branch represents signal objects by comparing the pairwise similarity of its feature node value and the corresponding feature values of the signal object sequentially. I just want to show the feature pattern tree. So here, this is an example of MFET, multimedia feature pattern tree. Here, this has branches. These are the feature nodes. This feature node value, whenever you want to represent any multimedia document, the multimedia objects feature values are compared with the feature nodes feature values. If it is within this threshold, that will be represented by the same branch. So when the branch feature node value is similar to signal object feature, the signal object is represented by that branch and the minimum of the feature and the feature node values assigned to the feature node. The pairwise similarity is evaluated based on the user-defined object similarity threshold. In this way, we'll construct this MFE. This paper is already present. Already, this work is already published. So this work we expect to extract the sequential multimedia feature patterns. Okay, so since each branch of the tree represent the features sequentially, so we use the branches to extract the sequential multimedia feature patterns. The sequential feature patterns of the multimedia documents are termed as sequential multimedia feature patterns, as the patterns are formed by the sequential features of multimedia objects. So, sequential multimedia feature patterns (SMFPs) are extracted from MFP branches. The length of the SMFP is defined as the number of sequential features in the SMFP. As the features determine the characteristics of the multimedia objects, the different length of SMFP describe the different multimedia objects. The SMFPs of different length may describe the multimedia documents of different topics. For example, with the multimedia documents of animals, the SMFP describing black color retrieves multimedia documents of black animals. The SMFP describing black and orange color retrieves the multimedia documents of animals with black and orange color, such as tiger, cats, and leopards. So, therefore, the SMFPs assist the mining methods by providing the minimal information required for knowledge mining from multimedia documents. So in the example given, if the length of the SMF is 5 and the user-defined minimum support is 2, this user-defined minimum support is the number of documents that the MFPT branch holds. So we extracted 6 SMFP for the data set of 6 documents. Here the the uh, left side represents the sequential multimedia features and the right side represent the labels of the multimedia documents. 1, 2, 3 means it is the multimedia document 1, 2 and 3. So the SMFPs are used to extract the multimedia class sequential rules. The SMFPs are labeled by the class label as I showed earlier. The right side shows the class labels of the multimedia documents. So these are used to generate the multimedia class sequential rules that are used for the classification of multimedia documents. The support of the rule can be defined as the number of UMDs that contain the sequential feature and are labeled with the class C. The occurrence of the rule can be defined as the number of UMDs that contain the sequential feature patterns presenting the rule's antecedent part. So the confidence of the rule can be defined as the support divided by the ratio of the support and the occurrence of the multimedia multimedia sequential class rules. The number of SMPs depend on the user-defined minimum support and the length of the SMLP. Each SMFP, that means each sequential multimedia feature pattern, it generates only one multimedia class sequential rule. So in a multimedia class sequential rule, the SMFPs are the antecedent part, whereas the class label of the UMDs that own the SMFP is the consequent part. So if more than one class label is designated to MCSR, then the class label that has more documents satisfying the MCSR will be assigned. In the example, in the example, let will decide C1 and C2 are the class label of the UMDs 1, 2, 3 and 4, 5, 6. So the MCSR generated from the MFPT are based on this. If you see, go back and see. So this is 1, 2, 3. This belongs to class 1, and this also belongs to class 1. This also belongs to class 2. This also belongs to class 1. But this belongs to class 1 and 2 because 3 belongs to class 1 and 4, 5, 6 are class 2, and all other 3 MCSR belongs to class 2. So for the MCSR 0, that is the for the MCSR this which is having class 1 and class 2, but we can consider this particular MCR belongs to class 2. Why? Because we have more documents related to class 2. Only since we are having only one document 3 belongs to class 1. For the classification, what we need to do is initially the training UMDs are represented by the MFFP and we need to extract the MCSR. Similarly, we represent the query UMD by the MFP and we'll extract the query MCSR. Then we'll compare the query MCSR antecedent part with the training MCSR antecedent part. Then we'll which MCSR, which training MCSR has maximum maximum objects of query MCSR, that label will assign this to query MCSR. So for example here, if the query document has S34, signal object 34, this signal object can be anything. Since as we said, the document representation, the multimedia to signal conversion, it converts all the images or it may be a audio or it may be a text. It will convert everything to signal object. So signal 34 can be a signal or image or can be anything. So just imagine we have 4 signal objects here and we'll these are the features of the signal object, and these features will be compared with the sequential features of the training MCSR. So while comparing, we'll get like class label C2. Okay, if you see here training MCS, we can see here. While comparing these features with this, we'll get class label C2 is selected for the query MD as it has a more query object. See, okay, C2 has more query objects of the, so that's why we assign the C2 for the query multimedia document. For the experiment, we used four data set, that is MDS1 and MDS2, and the Flickr data set. The Flickr data set is a subset of MIR Flickr 25K data set. From that, we selected 1,200 documents of 10 categories. Then we prepared one data set of FMDS of 1,000 multimedia documents for 20 concepts, which contains real images, audio, sounds, and text documents. All this we picked from the internet. So for the experiments, we have taken the object feedback threshold in 0, 1 in percentage as 0, 1, 3, 5, 7, 10, 13, 15, 20. And all the experiments are conducted with the different lengths of SMFEs. The length of SMFE, that is sequential multiple feature pattern, is from 60 to 100% we have taken as a threshold. So in the I think in the graph shows the various length of SMFEs are generated from the MFE representative for various object similarity threshold. We can see here, it is observed that the number of SMFEs extracted for each data set depends on the number of multimedia objects contained by the multimedia documents. The maximum number of SMFEs extracted for MDS1 is 449 and MDS2 is 1,475. Flickr 6,425, and the MDDS it is 3,869. The minimum number of SMFs extracted are MDS1 139, MDS2 417, Flickr 1389, and MDDS 1047. That is the reason, because MDS1 contains only the image and text, and MDS2 contains the audios and text. Flickr contains again the text and images, but only the MDTS dataset we have three types of data: images, 3D images, as well as audios and the text. The MCRs generated from the SMBs are used for the multimedia documents classification. The four data sets are divided in the ratio 80% to 20% from the training to form the training and query data set. The accuracy for all the query data sets are computed and the results are shown in the figure. So it is observed that the optimal SFMP length at which maximum accuracy is obtained is different for different data sets. The maximum accuracy obtained are 0.771 for MDS1 with 80% of SMFP length, and 0.866 for MDS2 with 90% of SMFP length, and 0.805 for Flickr with 90%, and 0.925 for MDS with 90% of SMFP length. So that's in future what we need is like the method for defining the dynamic optimal length need to be explored here. The maximum accuracy of MCR-based classification is compared with the maximum accuracy of multimedia class association, MCR-based classification and MFFT-based classification. The reason we selected these two classifiers for comparison is these classifiers use the same data sets and these are using the multimedia documents with all the three multimedia objects. The MCR-based classification achieved the accuracy improvement of 10% in MDS1, 3% in MDS2, 12% for Flickr, and 2% for MDDS, compared to MCR-based classification and 1% for MDS2 and 1% for Flickr compared to MFET-based classification. variation of result is due to the use of sequential features of different length by the SMFE classification, whereas MFFT considers all the similar features of signal objects. So we used the SMFEs, that means sequential multimedia feature patterns, for the retrieval of the multimedia document. For the experiment, we compared with the SMMD method and EMDR method. So the SMFE based retrieval outperforms the SMMD method with the maximum precision improvement of 12% for MDS1. Internal queries and 1% for MDS1 and 1% for MDS2. This method, the SMMD and EMDR, these methods are used only two datasets, MDS1, MDS2. So we compared the performance of our SMFP based multimedia document retrieval with for only two document datasets. In order to achieve the MMDs, the SMMD and the UMDR methods were constructed a multimodal feature space using Laplacian eigenmaps based on the unimodal similarity matrix. This similarity matrix is created using the equal number of neighbors for each modality. However, the multimedia objects of different modality may have different number of neighbors. That is the reason our method performs better compared to the SMMD and EMDR method. So finally, to conclude, we propose the sequential multimedia pattern mining to extract the knowledge from multimedia document. The branches of the MFFT representation are used to extract the MFFTs. So the MFFs are used to extract the MCSR, which are used for the classification of EMDs. The proposed MCR-based classification achieved significant improvement over MCAR-based classification and MFFT-based classification of multimedia documents. So in future, the proposed mining methods are dealing with only the text, image, and the audios. But actually, we need to work with the multiple documents along with this videos and animations. Also, an algorithm need to be developed to find the optimal length of SMFPs such that the minimum optimal length of SMFP define the complete characteristics of the multimedia object it denotes. So thank you. Any questions? These are the references we used for our research.
Thank you,
Thank you,
Pushpita,
sir.
for the nice talk. Are we having any questions from the audience? If not, then let's thank speaker again. And
Okay, thank you, sir.
yeah. And we'll move to the third talk of the session, which is quantifying hyperparameter leakage in machine learning. And over to the speaker now.
Hi, thanks.
Vasis, you should be able to share your screen.
Yes, just so is it visible?
Yeah.
Yes.
Okay, so let me just put it in full screen. Still visible?
Yeah, it is visible.
In full screen. Okay. I'll start then. Hello everyone, my name is Vasish Dudu. I'm currently a graduate student at the University of Waterloo's CRISP group, which is Cryptography, Security and Privacy. This was a work that I did during my undergraduate at IIIT Delhi in collaboration with Dr. Vijay Rao, who's a scientist at the Indian Defense Research and Development Organization. So the problem that we look at here is that of trying to consolidate different model extraction attacks in machine learning, where you aim to reverse engineer a target machine learning model into a mathematical framework such that you're able to quantify the leakage, and that helps you to evaluate the efficacy of different attacks. So just one sec. So I'll go over the introduction, then talk about the model extraction attacks. Then I'll basically introduce what the problem is for the current model extraction attacks and motivate why we need a mathematical framework to evaluate the model extraction attacks, and talk about Airavata, which is the proposed framework based on Bayesian networks. And finally, talk about our evaluation and conclusions. Machine learning models are an intellectual property for a company, and the reason is that typically it takes significant amount of time to design a machine learning model, and this is specifically so the case for neural networks, which has a large number of hyperparameters. So if you look at the design of a neural network, you have to select the number of layers, and there are different types of layers, and each layer has a different number of hyperparameters, and each hyperparameter has different options for you to select, different values that you can select. So when you put them all together, the search space for a neural network is intractable. And hence when a designer wants to design a neural network for a particular task, it's typically a multi-stage process, and hence when the final model is chosen, then that is typically that constitutes as an intellectual property of a company, and hence most of these models are considered as a black box in a machine learning system, in basically any deployed scenario. So there are two main deployment scenarios that we consider. One is the hardware accelerators, where you have the trained neural network and you have deployed them on an inference engine, and that inference engine is part of a bigger system, and you have an API through which you can basically the other subsystems or subcomponents can communicate with this particular inference engine by sending an input and get a corresponding prediction and use it for their own decision making. The second is that of machine learning as a service, where you see that the trained neural network is deployed on the on cloud, and there is an API access that is given to the users such that the user can send an input and get the corresponding predictions at some cost. And this has been monetized and commercialized by various companies such as Amazon Web Services, Google, Microsoft, and BigML. So in both these settings, there are significant security and privacy risks, but we specifically focus on the privacy risk of model extraction attacks. So an end-to-end model extraction attack is where the adversary tries to reconstruct or train a substitute model with similar architecture and functionality to the victim model. So you have the victim trained model deployed in one of the previously two described scenarios, and you want to come up with an architecture. You want to find an architecture which is close to the victim model's architecture, and you want to make sure that the functionality is same. So the end-to-end model extraction attack, the first step is to go and infer what the architecture looks like, or an approximate architecture. So the idea here is to reduce the large search space that you have for neural networks and find an approximate architecture. Luckily, we have the option that multiple architectures can have similar functionality. So you can have a larger model and maybe a smaller model with different hyperparameters, but they still can be trained with similar functionality measured in some metrics such as test accuracy. So here the attacks are mainly two types. One is the side channel attacks, where the adversary is assumed to have physical access to the hardware accelerator or any hardware that is running the neural network, and through side channels such as power consumption during the execution or the memory access patterns and so on, you are able to infer what the hyperparameters look like. And the second is a machine learning based attack that was proposed in ICLR, I think, a couple of years back, which uses machine learning models as attack tool to map the input output of the victim model to predict what the attributes of the target model might look like. The second step, once you have an approximate architecture coming from step one, is to then steal the functionality. And by stealing the functionality, I mean that when you pass the same input to the target model or the victim model and the substitute model, which is being controlled by the attacker, which has been inferred by the attacker, the output prediction should be close to each other. And here you have attacks which are remote. You don't necessarily require a physical access, and the remote API based attacks. So the initial set of attacks that were proposed include equation solving, where you have some unknowns and some known values, and you solve a system of linear equations. The second option is which is more popular these days, is that of active learning, where you send multiple inputs to the victim model, get the corresponding predictions, and create a synthetic data set with this input output pair to train the substitute model. So this is in some way similar to knowledge distillation that was proposed by Jeffrey Hinton, but the difference being, the main difference being that the data that is coming from is not from the same distribution as the victim model's training data, because the adversary might not know what the training data looks like. So you need to create, so you either can assume that you're using some publicly available image data set or publicly available data set. And the second option is to say that I'm going to use a maybe slightly skewed version of, or a slightly different distribution from which the victim model's training data set was taken. Keeping in mind these attacks, we go back to the problem with looking at each of these attacks. So if we consider just the stealing attack, the papers typically consider the previous or the architecture to be known. So they assume the architecture is known, and then they go on to look at algorithms to ensure that the functionality gets better or more similar as possible. Here the problem of model extraction attacks in general is similar to the story of the elephant and the blind man. So there are a bunch of blind men who are told to go and identify what an animal is by holding on to one part of the animal. And the problem, however, is that unless and until you combine the information that comes from all of that, you won't be able to get a good picture of the entire elephant. So each of these attack probes are basically like one of these blind men that go and infer one particular attribute of the neural network. But identifying the rest of the neural network is still a big search problem, and you still don't know how much have you extracted of the total model. And so this can be viewed as as from the information theory perspective, where you say that there is some entropy or of the black box model, and by each attack you're reducing that entropy and gaining some information. And so how much or what is the extent to which you can know what or how close is the substitute model to the target model. So to motivate that, we look at two problems in extraction, or two sources of uncertainty in extraction. One is that when you perform an attack, something like machine learning based attack, you infer some attribute, but that attribute is being inferred with some confidence, but not 100% accuracy. So there's some degree of confidence in the way you infer it. The second is when you do the second step of stealing the functionality, you typically train the model on the synthetic data set. And that training itself is a stochastic process. So in that particular case, it is, again, you have, so if you train the same model twice under the same hyperparameters, there's going to be small variations. So keeping those two uncertainties, you know that it's difficult to extract the exact model as the target model. So what is the total extent of extraction? And knowing or answering this question can help us to understand the relative threats of these reverse engineering attacks for neural networks, and also from the attacker's perspective, help to identify the optimal combination that can lead to a higher success rate. And from a defender's perspective, you can allocate resources by identifying the most prominent attack and setting up defenses to protect against those. So here we start to look at the motivation for the framework. And so if we want to analyze different attacks, it's it's huge because it takes a lot of resources and time. For instance, if I just consider side channel based attacks, then you require equipment which is expensive. And typically that would involve you to have an oscillator, probes, and so on. And if you look at the case of machine learning based attack, then the paper that proposed the machine learning attack ran around for a simple 7-layer architecture. In order to infer that architecture, they had to train the attack models for around 40 GPU days. So that's too much time for you to generate empirical data. So that results in some requirements for the design of the theoretical model that we're coming up with. And one is that of limited data. So you don't have a lot of empirical data available. So you just need to make use of whatever information possibly the attack and the inferred attributes are. So just by looking at what the attack is and the inferred attributes, can you come up with something? The second is that the theoretical model should be able to capture a static adversary, which means that given in all these extraction attacks, the assumption is that the adversary performs an attack and you are able to infer a particular attribute from it, and you won't learn anything more than what was predefined by the attack for inference. For instance, if you're using timing side channel in a black box setting, it turns out you're able to infer the total number of layers in the neural network. But whatever the value of that number of layers is, it doesn't. It's something that's dependent on the model. But then the only thing that you'll be inferring is the total number of layers. So, as an implication of that, you have model agnostic, where you say that despite whatever the model features vary, I should still be able to get information which is fairly reliable, and the relative threat should not vary with regards to the model information. And finally, the architecture or the framework that we're looking at should be flexible, because let's say there are new attacks that are coming up, or new architectures that are coming up, or new domains. You should be able to capture all of this as part of your framework. So there we use Bayesian networks in order to address this. So Bayesian networks are directed acyclic graphs, and these are graphical models which capture causal relationship between different random variables. So this is a subjective approach of looking at probability, where you say that I have some belief on an event occurring, rather than looking at the frequentist notion of probability, where I say that what is the favorable number of outcomes over the total number of outcomes. And that works in the case of where you have enough data, but since we don't have that amount of data in this particular case, it's better to look at the subjective notion of probability. So the Bayesian network captures the joint probability across all the random variables that is part of the graph. And once you have the joint probability, then during the inference, you want to identify what the conditional probability for a particular variable is by breaking that joint probability into different factors. So the training of the Bayesian network parameters, which is the conditional probability, is done using the Bayes rule. So as part of the Airavata framework, so this is the kind of Bayesian network we use, and we model the attacks and defenses as cause-effect relationships. So as soon as an adversary chooses to perform one attack, there are certain attributes that are inferred, and this data set is created, or the synthetic data set is created based on the previous research papers that indicate the different attacks. So for instance, there is timing side channel, there is power side channel, there is machine learning based attacks, and there is the hardware side channel, which encompasses cache side channels and memory side channels and so on. So each of these attacks results in inferring different parameters, and and the conditional probability that is associated with different variables indicates the success of the attack for that underlying values that might vary. So with that, so here we consider all the variables to be binary, at least the attacks and the attribute variables. So if you perform an attack, then the columns corresponding to the attributes are set to 1. And those attributes which are not inferred are set to 0. So based on the combination of attacks that are being used by an adversary, you can correspondingly look at the total number of inferred attributes. And based on that, we use a subjective threshold. which can be tuned because it's a more generic theoretical model that allows you to have some flexibility to design according to your application. So there we say that if all the attributes are inferred, then it's in the class of high model extraction or high degree of knowledge inferred. And if it's somewhere between 3 to 5, then it's set as medium. And if it's less than 3, then we say that the extraction degree is low, or the knowledge inferred by the adversary is low. So within this, we have to consider different adversary models because not all attacks are applicable in all scenarios. So for that, we consider the first adversary who has a remote access, and that goes back to the first slide in the introduction, which says machine learning as a service, where you have the API access and you send some query and you get the predictions back. And in that kind of setting, the attacks could include the machine learning based attack with multiple meta models or functionality stealing. The second adversary we consider is that based on physical access to the hardware running the model, and that will allow you to perform various side channel attacks. And finally, the idea is to combine both of these and say that there could be an insider machine learning as a service provider who has access to the hardware and has access to the API. So in such scenarios, you can combine both the attacks and look at all the attacks in unison. So for the evaluation, this is the results that we get for attack 1. And we see that so the scores corresponding to combining different attacks is higher for the high category compared to the other. One interesting, and this is for attack 2, attack 3, and so here we basically see that in case of timing side channels, the results are with and without the timing side channel, the scores are same because side channels basically infer the total number of layers in a black box setting. And if that's the case, then you don't, that is something also being inferred by the other attacks as well. So as such, timing side channel is not contributing any additional information, and hence the knowledge that you get is similar. In case of adversary 2, both the attacks typically lie in the medium range because they're just able to infer the architectural details in good granularity, but they're not able to infer what the parameters or functionalities because that access is not there with the adversary. Finally, when we combine all of them, we see that there are so hardware side channels, which is basically cache memory based and so on, combined with the functionality stealing, which allows you to infer the parameters, gives the best performance compared to other attacks. So you don't need to perform all the attacks, but then there are some attacks which work well, and that invariably reduces the effort from the adversary. So in conclusion, we propose Airavata, which is a framework based on Bayesian networks, and that is a good tool for you to understand the relative threats of different attacks without actually having to perform an attack. And then that also enables you to identify the set of optimal attacks in an adversary setting to maximize the leakage. And the leakage, and the result that we see is that the leakage from a combination of attacks is much better than instead of looking at individual attacks. And with that, any questions?
Yeah. Thank you, Vasisht, for the nice talk. Any question from the audience? If not, then let's thank speaker again. And then we'll move to the final talk of the session, which is efficient compression algorithm for multimedia data. So over to Karthik.
Can anyone enable? Okay. Can you see my screen?
Yeah, so maybe you can zoom. Yeah, right.
Okay. Good afternoon, all. This is Karthik. I'm currently part of data science team at CRED. Today, I'm here to present our work on efficient compression algorithm for multimedia data. with the advent of internet, we are generating a lot of multimedia data, which is of high dimension, and its size has exceeded memory capacity of the systems. These are some of the widely adopted formats for representing multimedia data. Here are the popular similarity measures that are used for computing similarity between two vectors. However, due to curse of dimensionality, brute force way of computing similarity is not efficient. There is a fundamental need for reducing dimensions, as these similarity subroutines are called multiple times. This dimensionality reduction not only decreases our computation cost, but it also saves space. One additional benefit is we can tune out less important information, and it serves as a regularization technique. Our focus here in this work is on sparse binary multimedia data. The words, for example, if we take text, word frequency within documents follows power law, and most of the words occur rarely in a document. So there is an opportunity for us to reduce dimension without losing essential information. This holds true for bag of visual words and user item interaction also. Here we present BCS, which is a simple and efficient algorithm for compressing sparse binary data. Our algorithm is binary to binary, and in our earlier work, we show that BCS preserves multiple similarity measures like inner product, Jaccard, and Hamming distance in one shot. In this work, we show that it works on cosine too. Advantages our approach is it is fast, space efficient as it's binary, and requires less random bits. Our core idea is simple, it's just bucketing plus XOR. We partition the coordinates into k buckets randomly, and for each of the k buckets, and for each of the elements within k buckets, we take the XOR of bits. So I'll illustrate with an example. In this example, our input vector, the image you see here on left side is our input vector. It is of dimension 10, and our reduced dimension is 3. So we choose one among B1, B2, B3 randomly 10 times. So we choose only 3 because our reduced dimension is 3. So whenever we have collisions, in that bucket, we sum up the elements and do mod 2. Given a pair of binary vectors ui and uj of dimension d and sparsity psi, we compress them using BCS and get ui dash and uj dash. If our compressed dimension is of order psi square, then cosine similarity of ui uj and their compressed representations would be approximately equal. So these are our experiment results. We perform two types of experiments, MAC and ranking, and we evaluate that on 4 public data sets of varying dimensions and show that our algorithm works across dimensions. You can also see the speed of BCS with other algorithms like SimHash, CVE, and MinHash. We are roughly 100 times most faster than the other algorithms. So we run two types of algorithms, MAC and ranking. In MAC, what we do is we just plot the difference of similarity between original vector and the compressed vectors. So red line is BCS. So here we have taken negative log of MAC. So higher negative log, lower is the MAC. You can see that BCS is as good as MinHash in many cases and even better on higher thresholds. So these are our results on ranking. In ranking, we split into buckets based on similarity. So if they fall into same bucket before and after compression, then BCS is doing a good job. So we compute precision, accuracy, and recall based on that. Even in ranking, we can see that BCS is doing as good as MinHash. To summarize, we improve running time, improve storage space, match benchmark accuracy, sometimes even better than them on downstream evaluation. These are some of the applications of our algorithm. Though there are methods like word-to-vec, LSH is still useful as it's extremely fast. LSH algorithms would be very useful in extreme classification where our label set becomes large and computing similarity becomes costly. We can speed them up by approximating them. So yeah, that's it. Thank you.
Thanks, Karthik, for the talk. Any question from the audience? So if not, then let's thank speaker again. So with this talk, we'll complete this session, and we'll take a break for lunch, and then we'll resume again from 2 p.m. for the short paper content analysis for the session 10A, which is short paper content analysis.